Can additive manufacturing play a role in nuclear power? The first 3D printed part in a nuclear reactor on the Cool Parts Show.
This episode of the Cool Parts Show is brought to you by Carpenter Additive.
We're at the company's powder production facility in Athens, Alabama.
Specifically, we are standing on top of the Z1, the company's largest vacuum atomizer for producing metal powders.
Want to know how to make metal powder for additive manufacturing? Stick around after the episode. I'm Pete.
I'm Stephanie.
Welcome to the Cool Parts Show.
This is our show all about cool, unique, interesting, possibly radioactive 3D printed parts.
Yeah, we'll get to that. We're at Oak Ridge National Lab. We're doing a variety of episodes on additive manufacturing successes being advanced by the Manufacturing Demonstration Facility.
We are standing in the Advanced Characterization Lab, the result of a partnership between Oak Ridge and Zeiss, and we're here to talk about one of our favorite topics.
A bracket. Seemingly simple part made through additive manufacturing, not as simple as it seems. We'll get into that. But first, Stephanie, why do we love brackets?
We love brackets because they are everywhere. They are these really functional parts that do all kinds of things to the point that we take them for granted. But when you pair them with 3D printing, they can be a really valuable and a really accessible case study for what it can do.
Additive manufacturing loves brackets. The typical off-the-shelf bracket almost always uses too much material for the function that it's asked to perform. Additive manufacturing, 3D printing, offers the way to more material-efficient, more mass-efficient brackets.
So usually when we talk about brackets in the context of 3D printing, we're looking at these things that look really topology optimized, very organic, and this bracket looks pretty conventional. So what's going on here?
Special bracket. This is a bracket for a nuclear reactor.
Should you be holding that?
Good question. So this isn't the actual bracket, but it is identical to a set of brackets currently in use in the Browns Ferry nuclear power plant in Alabama, making the sister parts to this component quite possibly the first 3D printed components to find use inside a nuclear power plant.
Okay, very cool. But what does this bracket do inside of a nuclear reactor?
This bracket helps to hold the fuel assembly in a reactor. Inside of a nuclear reactor, as you'd imagine, there are all of these hardware systems and safeguards that protect against various risks, including some very unlikely risks, and that sort of describes the use of this bracket. It is part of the system that protects against extreme vibrations, like if the power plant experienced an earthquake, say. So why don't I introduce Ryan Dehoff? He is Deposition Science and Technology Group Leader here at Oak Ridge, and he can explain in more detail.
So inside of a nuclear reactor, you have something called a fuel assembly bundle. And these are basically bundles that are filled with nuclear fuel that are then inserted into the reactor. And this bracket plays a role of keeping those bundles in the right location inside of the reactor, making sure that vibrations and movement are minimized during operation. And so they're effectively responsible for helping to make sure that the reactor functions properly. Framatome actually owns these fuel assembly bundles that go inside of the nuclear reactor for the Tennessee Valley Authority. And so Framatome is really the one that is responsible for the operation of these assemblies and these brackets inside of an actual reactor. And so as part of this project, they're the ones that helped us to outline the metrics that had to be achieved, the performance specifications, tolerances, and certification of qualification, because if something goes wrong, they are the responsible party over the work. And so they have to ensure that these brackets are capable of performing.
So this unassuming bracket is actually pretty important to the proper operation of the nuclear reactor in the event of some kind of accident. So tell me more, how was this 3D printed?
3D printed in 316 stainless steel, laser powder bed fusion on a machine from Concept Laser, but 3D printing is not the entire process.
The challenge is that the geometric accuracy and tolerances required for this component were significantly greater than what can be achieved currently today in that 3D printing process. And so we had to go through and figure out how to machine the part after we printed it in order to maintain that geometric accuracy that we required on the component. So we used a combination of printing, machining, and post-finishing in order to achieve the actual final component.
So that answers how this was made, but I still don't really know why. Why would you want to 3D print the first bracket to go into a nuclear reactor?
Right, so additive manufacturing is transformative, but it is not the right solution for every part. Why make this part through 3D printing? Why make it additively? So the material is part of the answer to that. This is 316 stainless steel. So that is a material that has been accepted for use in the nuclear power industry, and a material that we know very well how to 3D print effectively, how to produce through laser powder bed fusion. So that set of circumstances kind of created the opening to apply additive manufacturing for making this part. And that's really the reason why. It's not just about this part, but it's about additive manufacturing. Additive 3D printing holds a lot of promise for the nuclear power industry, and this component is possibly the beginning of that. Ryan has more to say about that.
Yeah, so I think everybody knows the potential that additive manufacturing technology has, right? We have the ability to build extremely complex geometries, and essentially a nuclear reactor is a very, very large scale heat exchanger. And so additive manufacturing enables you to be able to print these very complicated and complex designs. And so I think that there could be a very, very large impact in additive manufacturing technologies inside of the nuclear industry. The challenge is that we do have to certify and qualify components. Now, there's people in the industry that have certified and qualified components in the medical industry. We've seen aerospace. And so I think the next thing is kind of nuclear. And if we can certify and qualify parts to go inside of a nuclear reactor, I think that we can certify and qualify parts to do nearly anything.
So that's really the challenge. The nuclear power industry is characterized by a lot of certification requirements, a lot of controls. It's a very conservative industry, as you would want it to be. So this component offered the chance not just to prove out 3D printing in a part that goes into a reactor, but also to pioneer the process for how you certify an additively manufactured part. And it turns out additive manufacturing not only brings the promise of a lot of new design freedoms for nuclear power components, but also potentially a new level of capability when it comes to certifying parts.
So part of what's really interesting about this bracket is that just for the sake of getting a 3D printed part into a nuclear reactor that could be certified, they took all the other variables out of this. So we know the design of the existing bracket, let's keep that exactly the same. We know the material that works in this application, let's use the same material. And so really what we're testing here is just the additive manufacturing process. Can 3D printing deliver an equivalent bracket?
So that's right, and those constraints created the opportunity for additive. They're now working out the process, and part of that process involves developing a new mode of certifying a component.
I think the biggest challenge with the nuclear industry is certification and qualification, right? And this is something that has really hindered advanced manufacturing technologies from being implemented into the nuclear industry holistically. Part of that challenge is we really need to understand how that material is going to perform in service. What we have done here at Oak Ridge is come up with a digital platform for the additive manufacturing technology that combines in situ process monitoring, computer vision, in situ sensing. All of that goes into a digital platform that we can help to aid the certification and qualification process. We combine that with post-inspection data, material properties, microstructure analysis, and all of that goes into a digital package that could be used to certify and qualify components significantly cheaper than what we do today. Unfortunately, with this process, we haven't proven that technology in the nuclear industry yet today. And so with this particular bracket, what we did is we certified and qualified it using that digital platform that we've been developing. But we've also certified and qualified it using the conventional processes that have been established for many, many years here at Oak Ridge and with Framatome. And they then certified and qualified that to go into the reactor. And so we really certified it twice in a way. And really what we're trying to do is see if that digital platform could eventually replace the conventional inspection technologies at a much, much cheaper cost.
So at this point, Oak Ridge has produced some of these brackets, they've certified them, there are some in the nuclear reactor. How long until we know if this worked?
6 years. That particular reactor will next see maintenance service in 6 years. At that point, these 3D printed brackets will be removed. They'll go back to Oak Ridge, and the researchers here will look at them closely, study them closely to determine that these components performed just as well as conventionally manufactured brackets.
And so once that happens, if we find that the brackets performed as expected, what could that mean for nuclear reactors and the energy industry?
2 things. One, the design freedoms of additive manufacturing brought to the nuclear power industry, and that means potentially more geometrically efficient parts, more cost and material efficient parts, maybe better performing components. That's one. But another is with this direct digital manufacturing process, additive manufacturing, there is the potential for a more efficient and capable certification process, a digitally enabled certification process.
Okay, I think I got this.
All right, take it.
So this is a bracket produced by Oak Ridge for Framatome. It is part of the fuel assembly for a nuclear reactor. Specifically, it protects against vibration. It was 3D printed using laser powder bed fusion on a concept laser machine. It is made out of 316 stainless steel. And part of what's interesting about this bracket is that the design is the original design of the existing component. The material is one that's already in use in nuclear reactors. And really what they were testing here is just, can you put a 3D printed bracket into a nuclear reactor and expect the same kind of performance as you would from a conventional bracket? So this part was 3D printed, it had some finish machining, it was inspected here in this lab, and it was also certified in 2 different ways. It went through a conventional certification process as well as a new digital certification process, which could be a faster, easier, cheaper way of certifying parts like this in the future. Some of these brackets are in a nuclear reactor now. They will stay there for 6 years, and then they'll come back to Oak Ridge. They'll be able to study and analyze the performance and see if 3D printing can really hold up in a nuclear reactor.
That'll do it. If you have a cool part to share, if you have a cool bracket to share, email us, coolparts@additivemanufacturing.media.
Thank you again to our hosts at Oak Ridge. If you want to see all the episodes that we are filming here at the MDF, you can find them on our YouTube channel or at thecoolpartshow.com.
If you like the show, leave a comment. Be sure to subscribe. Thank you for watching. This episode's brought to you by Carpenter Additive. We are at the company's powder production facility in Athens, Alabama, and we are standing on top of an atomizer. The Z1 is Carpenter Technology's largest vacuum atomizer, and it is the heart of the process for making additive manufacturing metal powder here at Carpenter Additive.
This facility is capable of producing up to 18,000 pounds of metal powder per day. Plant manager Jordan Ralph talked us through the process.
So an atomizer is a piece of equipment that is capable of melting and pouring molten metal into the stream of high pressure gas that turns that molten metal into tiny, tiny droplets that ultimately cool and form our powder, which looks like gray dust. So to start our process and the ultimate end-to-end solution that we have here, we bring in raw materials all the way down to individual elements, so nickel, cobalt, chrome, moly, niobium. We bring all of those raw materials into the shop. We utilize those materials to build charges that go into the atomizer. As you walk that flow path, you run through our charge makeup area where all of the materials are weighed out in very exact quantities. That ensures that we're able to hit our customer specifications and hold the tight tolerances that we're looking for on a chemistry perspective. From there, the material is flown to the top of the atomizer and charged into the furnace. As the material is produced, it's poured out and is collected at the bottom of the atomizer. The material is then taken and transferred into a bulk container for processing through the rest of the value stream. The next stop for any of our atomized powder would be the screener. So that will remove the coarse portion of the powder. From there, we take it through air classification. That takes the fine portion of the particle size distribution out and makes the final cut for an additive material, like a 10 to 45. From there, we stack up all of those individual lots and put them into the 12,000 pound blender to make the single homogeneous blends. At that point, we are able to pack in any configuration that the customer is looking for, whether that be drums, bottles, powder trace hoppers. Really, we've got a lot of options to meet customers' needs there. The atomization capability in all of the powder capabilities gives us a unique position where we're actually able to produce the powder, run testing through additive machines all the way through HIP and heat treat, do final testing on those products, and then make additional changes or try to optimize things like our chemistry or sizing so that we ultimately can serve our customers better.